Light and matter interact with each other, and this is sort of the ongoing theme of this series of videos about atomic structure. And something that we looked at in a previous video was that if you take a macroscopic object like a rock and you get it really hot, it'll start glowing. And the pattern of light that's emitted by a hot object is called blackbody radiation. And you can take the light that's emitted by something like glowing lava at 1,000 kelvins and pass that light through a prism and split it up into its constituent colors. You can also reflect the light off of a diffraction surface, like the surface of a DVD, or you can use a diffraction grating, like in this spectroscope. And any of these devices will split the light that's emitted by something like hot lava, split it up into a spectrum like this, where you can see a continuous pattern of colors that are emitted by this hot object. And if you heat an object to higher temperatures, you see the same thing, except the pattern of colors shifts a little bit. For a tungsten filament in an incandescent light bulb at 3,000 kelvins, you start to see more yellows, greens, and blues in the spectrum. And by the time you get to a very hot object, such as the surface of the sun at 6,000 kelvins, the glow encompasses the entire visual range of the spectrum, and you see all of the colors glowing intensely. And so this pattern is characteristic of macroscopic objects like rocks, or tungsten wires, or the sun, and insofar as you see this continuous spectrum of light that's emitted. Now, something very different happens if you, rather than looking at a macroscopic object that's heated up, if you take individual atoms and heat them up until they glow. And you can do this in something called a discharge tube. This is just a glass tube that's been filled with a gas. This particular tube is filled with hydrogen gas. And if you apply a high voltage, typically 1,000 volts, that will heat up the gas to the point that the hydrogen molecules split apart into individual atoms, and those hot atoms will glow in the same way that hot lava glows, or a hot tungsten filament glows, or the hot surface of the sun glows. And so when you do that in this hydrogen lamp, you see a distinctive purplish color that's in the middle of this photograph. And if you take that purplish glow and pass it through a prism or a spectroscope, this is what you see. It's very different from the continuous spectrum of blackbody radiation. Instead, you just get discrete lines at particular colors. So we see one line in the red part of the spectrum, another line that's sort of cyan, another that's blue, and another that is violet. And similar things happen with other kinds of atoms. So if you take a discharge tube full of helium and get it hot, this is what it looks like. You see another pattern with discrete lines at particular colors in the spectrum. Mercury does the same thing. In fact, every element produces its own unique spectrum of lines. And you can use this to identify elements. If you don't know what is in a sample, you can vaporize it, get it really hot, and look at the light coming off of the hot atoms. And if you match up the lines that you see against these spectral fingerprints, you can figure out what you've got in an unknown sample. And you can measure the wavelengths of this light very precisely. So for instance, for hydrogen, the red line is at 656.3 nanometers, the cyan line is at 486.1, and so on. And I want to look a little more closely at this hydrogen spectrum. And physicists were able to make these spectral measurements very precisely even before the 20th century. So in the late 1800s, physicists were able to observe these spectra. They were able to measure the wavelengths emitted by something like hydrogen atoms very precisely. And some effort went into looking for a pattern in these wavelengths. And so you have to understand that in the ever since Newton developed his laws of motion in the Age of Enlightenment, physicists have been enamored with the idea of a clockwork universe, where the universe was like a well-oiled machine that followed rigid mechanical principles. And if you could just figure out the patterns in nature, you could understand what makes the universe tick. And so um, so it's not too surprising that when this discrete pattern of hydrogen wavelengths that was discovered, a lot of people were interested in trying to tease out what the pattern was in these wavelengths. And in 1885, a fellow in Basel, Switzerland, Johann Jakob Balmer, um, took up the challenge. He was trained as a mathematician, and he looked at these spectral lines. And if you just look at the wavelengths by themselves, it's hard to see an obvious pattern. This is what it looks like if you make yourself a little graph of the wavelengths. But Balmer was convinced that there was some pattern in these wavelength numbers, that they had to mean something, and so he sort of played around with the numbers, and no one knows exactly how he went about tackling this puzzle, but it might have been something sort of like this. So we do know that he started off by rather than looking at the wavelengths themselves, he looked at the reciprocal of the wavelength. So 1 over the wavelength. This quantity is called the wave number, and it's related to the frequency of light. And if you plot these wave numbers, then, well, you still don't see an obvious pattern. But if you also take the reciprocal of the line number, so instead of 2, 3, 4, you have 1/2, 1/3, 1/4, then you start to see what looks like it might be a pattern. This is looking almost like a straight line. It's not a perfect straight line, but it's pretty close. And so we may be on the right track here. So something else that Balmer did was he played around with squaring some of these numbers, and in particular, if you square the index number of the line before you take the reciprocal, then instead of 1, 2, 3, 4, you get 1, and then 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. And if you make a graph of these numbers, well, that is starting to look a little worse. It doesn't look as straight. But eventually, Balmer tried shifting the wavelengths down by 2 positions, and then looking at the pattern. And when he did this, the points fell on a perfectly straight line. So this was remarkable. Balmer was really happy with this result. He didn't know what it meant, but this pattern was very exact. And if I blow this up a little bit so we can see a little better what's going on. So the mathematical pattern that Balmer found was that 1 over the wavelength is equal to a constant times 1/4 minus 1 over n squared, where n is 3 for the red line, n is 4 for the n is 3 for the violet line, n is 4 for the blue line, n is 5 for the cyan line, and n is 6 for the red line. Oh no, I think I got that backwards again. So the red line, 1 over 56.3 corresponds to 1 over 3 squared. And the cyan line corresponds to 1 over 4 squared. The blue line corresponds to 1 over 5 squared. The violet line corresponds to 1 over 6 squared. Yeah, I got that backwards a second ago. So Balmer saw that this line fit the observations perfectly, and he wondered if the pattern might continue. And in particular, he wondered if there would also be a line corresponding to 1 over 7 squared. If there were such a line, it would be at a wavelength of 397.0 nanometers. And now, such a line hadn't been observed, and if you were to look at the spectrum for hydrogen, the red line is very bright. The cyan line is a bit dimmer. The blue line is dimmer still. The violet line is quite faint and actually hard to see. But when actually astronomers went and looked more carefully at the spectrum for hydrogen, they found that actually there is an even dimmer violet line, and it is exactly where Balmer predicted, at 397.0 nanometers. And so that was still, nobody knew what the pattern meant, but it was clear that the pattern was real. So I'm going to clear out some of this cruft here and squish this down a little bit. And the reason I'm squishing it down is that the visible part of the spectrum that we've talked about so far is only a part of the electromagnetic spectrum as a whole. Beyond the visible spectrum, we have ultraviolet and infrared, and then it goes beyond that. And when it became possible in the early 20th century to do spectral measurements outside the visible spectrum, even more lines were discovered in glowing hydrogen. So in the ultraviolet part of the spectrum, these measurements were done from 1906 to 1914. There was another set of lines that were discovered, and if you take these lines and plot them on the graph the same way that Balmer did with the visible lines, those lines in the ultraviolet part of the spectrum actually form a new line that's parallel to the first line, and it corresponds to the same sort of pattern that Balmer found, except instead of 1 over 4 minus 1 over n squared, the pattern was 1 over 1 minus 1 over n squared. And then beginning in 1908, measurements were done in the infrared part of the spectrum, and even more lines were found in the spectrum of glowing hydrogen. And when these wavelengths were plotted in the same way, you get... And so when the infrared lines were plotted in the same way, they formed another line on this graph, again parallel to the first, and this matched a pattern with 1 over 9 minus 1 over n squared. And so even further out in the infrared spectrum, even more lines were discovered that corresponded to 1 over 16 minus 1 over n squared, 1 over 25 minus 1 over n squared. And what all of these sets of spectral lines, the pattern that they all have together is that they all satisfy that 1 over the wavelength is some constant times 1 over some some integer squared minus 1 over some other integer squared. And the this mathematical formula was put together by a fellow named Rydberg, and the constant here is named in his honor. It's called the Rydberg constant, and the Rydberg constant is actually one of the most precisely measured physical constants in the universe. Its value is 10,973,731.568160 per meter is the measured value for the Rydberg constant. And so I'm going to end this video here and pick up the thread of the story in the next one.